Alright, my name is Jason Porter, and I'm going to continue to talk on polypropylene fumarate. So my research study was development of nano and microscale composite 3D scaffolds using PPF, DEF, and HA with it for microcellular lithography. It was in the Microelectronic Engineering Journal and was based out of South Korea. So the specific scope of study was to basically the creation of the microscale PPF, DEF, HA scaffolds using microcellular lithography. And the key question is, are these scaffolds created biocompatible? So the experimental approach, they use basically a total of 4 different materials within it. And on the right is kind of the process and how they made it, starting with just the propylene glycol and the fumarate acid. So they did a 70-30 mix of propylene fumarate and diethyl fumarate. And then they added in bis-acrylphosphine oxide at 1% weight as a photoinitiator, and then hydroxyacetate as 7% for the biocompatibility to increase it. So the process conditions were both material composition. They did a PPF DEF and also PPF DEF HA, and then the cell growth. Characterization tools are the microcellular lithography and a scanning electron microscope. So the first result was just, can they actually make these scaffolds using this material base? And they were very successful with it. So the layer height were 2 by 215 micrometers. So basically each time the machine laid down a layer, it would be 215 micrometers, and then they'd do 2 in a row to get the actual layer height of each of the scaffolds. So there's 6 layers total, making 2.5 millimeters tall. And the line width was 125, and then the pore size, so the gap in between, was the range of 330 to 360 micrometers. And as you can see, they went with a staggered design, so where one layer would be like this, the next layer would be like that, and the next layer would be actually in between, so that would pour down accurately. And so from this we can determine that microcellular lithography can make scaffolds out of PPF, DEF, HA. So the next question is, are the PPF, DEF, HA or just the normal PPF, DEF scaffolds better? From this graph you can see that almost every single time the additive HA made it much better. And from just kind of taking rough images from the graph, we can see there's about a 40% difference between day 1, a 50% difference between day 4, 62% difference between day 7, and then a 27% difference between day 14. So what it means is originally you're going to have a much faster growth rate between the two, but after 14 days it's going to get a little bit closer overall. So on the long term they'll be about the same, but there still will be a difference. So once again, using HA with PPF DEF is better for biocompatibility than just the normal PPF DEF. Key conclusions are that the scaffolds can be made. Adding hydroxyacetate is better for biocompatibility. And a personal opinion of the paper is it would be good to have more. It was a good proof of concept of the technology and that it can actually create the parts. It would be better to have a better testing system for cell growth. What they currently use is just optical density using the scanning electron microscope. And then in vivo testing, because they proved it would work in vitro, but it would be nice to see in vivo just to see how it would work within a true living organism.